Okay, so my goal yesterday was to kind of describe two situations which they look different at the beginning, and then they had some similarities, right? So the first, it was in the stable homotopy theory, and it was the classification of the thick subcategories of the finite spectra, right? And they were just very well organized by using the Morava-K theories. So the Morava-K theories were used to test in which of the thick subcategories your finite spectra is, right? And they look like this. And then another example, which I was trying to describe, is that in the context of modular representation theory, you can kind of tune the category of modules to produce a category which is the stable module category, which had some similarities in the structure to the stable homotopy theory. It had this suspension, these shift functors, and you had the notion of exact sequence or co-fiber sequences. And using these techniques, it was also possible to classify the thick subcategories of the stable module category for KG. K will be FP each time I'm talking about a finite group. I didn't mention this at the result. It doesn't need, we can be more general, but let's keep this for simplicity, right? And that was in the modular representation theory, where the characteristic of the field divides the order of the group. And then there was also a bijection between these thick subcategories and some special subsets of the cohomology of G. Sorry, of the spectrum of the cohomology of G. Prox is just the spectrum of prime ideals, of homogeneous prime ideals in the cohomology of G, where you remove the maximal idea, the one which is just taking all elements of positive degree. Right? Okay, so my goal, and there are, this I will mention the work of Benson, Iyengar, and Krause, in which it was for any finite group, but I need to add some decorations to the left-hand side, right? So let me first give, trying to describe a context, yeah? Yeah. At this point, it's finite P group. But then for going with general groups, I need to add some decoration, so I will introduce some concepts just to do this. So let me, Blackboard. Okay. And the key definition today is what is a tensor triangulated tensor-triangulated category. And so let's start with describing the terms, right? So let's start with an additive category. So the set of morphisms have an abelian structure, they are abelian groups. And with a fixed equivalence, which is going to be called the shift or the suspension. And with this information, let me tell you what's a triangle in this category. So a triangle in T is a sequence of morphisms alpha, beta, gamma of these types. Alpha goes from X to Y, beta goes from Y to Z, and the last one, gamma, goes from Z to the suspension of X. Sometimes these exact triangles I also call co-fiber sequences in analogy with homotopy theory. What's a morphism? So a morphism is between triangles is what you imagine morphism between triangles is what it should be. So if you have another triangle, sorry, I try not to breathe, but it doesn't work. So it's are morphisms from x to x prime, y to y prime, the same for z, and the last one is just the suspension of this one, such that everything commutes. And so we have a notion of a triangle, a morphism between triangles. Inside that, you can also then decide when two triangles are isomorphic, when you have maps in both directions, giving the identity. And so now you can define what's a triangulated category. So we say that T is a triangulated category. If it is equipped with a class of distinguished triangles. Satisfying these distinguished triangles will be called exact triangles or just cofiber sequences. That's the terminology that we will use for these exact triangles. And satisfying, and then let me tell you the conditions that they will satisfy. Okay, first set of conditions is that so any triangle isomorphic to an exact triangle is exact. That's first one, it's closed under isomorphism of triangles. The second one is that this is an exact triangle. And each morphism fits into an exact triangle. You can make the analogy with homotopy theory in your head, right? So each morphism fits into an exact triangle. So you can always have, and then you can always complete F to an exact triangle. So yeah, that's the first set of conditions that they need to satisfy, and then alpha beta gamma is an exact triangle if only if beta gamma minus suspension alpha is so. So you have alpha, beta, gamma, but you can continue the sequence by taking suspension of alpha and minus suspension of alpha, and then so it says that this is an exact triangle if only if this is so. Right? And the third condition is about morphisms. If you have two exact triangles and you are given a morphism from x to x prime, y to y prime, such that the diagram closes, the condition says that there exist also a map here, and the suspension of you want, so such that this is a morphism of exact triangles. You can always complete a morphism of exact triangles when you have the first two morphisms. So there exist. Then, I mean, this commutes. Yeah. Then there exists this one such that describing a morphism between triangles. Between exact triangles. And the last one, I'm not going to write it down. It could be long. It's what it's called the Octahedral Axiom. Or sometimes it's called Verdier's Octahedral Axiom. I'm not going to describe it down. It's technical and it will not illuminate what's going to happen later, right? So you have a feeling of what's a triangulated category. So when I say what I mean by tensor. So I describe triangulated category, and let me say what I mean by tensor. So that will add a monoidal structure to the triangulated structure. So T is symmetric monoidal. If it's equipped with a functor from T, right? And with a unit, and it's symmetric. That means that there are natural isomorphisms between A tensor B and B tensor A when you just twist the coordinates in this functor, right? And then it satisfies the properties you could imagine just in the case of these examples yesterday, the smash product of spectra gives you a monoidal structure, and the tensor product of complex representations gives you monoidal structure, right? Which, yeah, let's say associative up to iso, and symmetric means commutative up to iso. Yeah, is symmetric means commutative up to all up to natural isomorphisms. Yeah. So now I have tensor and have triangulated, but when I put them together, I need some compatibility condition between these two structures. It's not going to be tensor on one side and triangulated on the other side. We need some compatibility, and this is what it's tensor triangulated. If it's symmetric monoidal, triangulated, and the compatibility goes by saying that this bifunctor, which describes the monoidal structure, is exact in both variables. That means that you have an exact sequence, one of those distinguished triangles, and when you, let me use this language, when you tensor with an object from any side, it's still exact. You have another triangle in your category. That's the compatibility. So, and tensor is exact. I didn't define what means exact. So a functor between two triangulated categories needs to take it's exact would take exact sequence to exact sequence. It means it's a functor between the two triangulated structures. So that means that this bifunctor has to respect these distinguished triangles in both variables. Okay, so that's what, so examples. Well, just the two examples I described to you before. I mean, before means last talk yesterday. Yeah. So examples. So I'm going to use this notation today instead of a spectrum. Maybe it's more standard now. That's SH for the category of a spectra, right? And so this is an example, and this is another example. Yeah. And I can remove fin, and I can write capital letters, and it's still. But let me just keep it this way. Well, okay, just. Yeah. And there are other examples. There's another example which I didn't mention yesterday because I don't want to introduce another type of categories, which is the derived category of a ring. So another example of classification of thick subcategories. I will just say it in words for those who have an idea of what I'm talking. So you have the derived category of a noetherian ring, a commutative noetherian ring. What you do is you just take, instead of taking modules, you take complexes. And then there is a notion of homotopy between complexes. So you can make an homotopy category of complexes. But then you can also do homology. So, and then that gives you a notion of quasi-isomorphism. So you have a morphism of complexes, a quasi-isomorphism, if it induces an iso-homology. So what you do is you compute this homotopy category, but inside this homotopy category, there are quasi-isomorphisms which are not homotopy equivalences, and then the last step to go to the derived category is to invert all quasi-isomorphisms. So in the derived category, it just goes by taking the homotopy category of complexes and then you invert quasi-isomorphisms. That's a very quick way of describing it. So Hopkins it has a triangulated structure, and Hopkins just also classify the thick subcategories of the category of perfect complexes. That means that the bounded complexes which are finitely generated, and also in correspondence with certain subsets of the spectrum of the ring, in the same way as similar to first example, but second example, but without a group G. Just nothing is graded, just you have modules of a noetherian ring. So I didn't mention this example because I didn't want to give more technology the first day. And let me give you a definition before I proceed. That we say that an object in T, but this is a more general definition, but is compact, or sometimes is small, if when you look at ohms T C dash, this functor, if this functor preserves filter colimits, that you can move the colimits from this outside, so that commutes with filtered colimits, right? So you can look at in a tensor-triangulated category, you can look at the subcategory of compact objects. And it turns out that this category is the subcategory of compact objects inside the stable homotopy category. And the finitely generated modules describe you the compact objects for the stable module category. So these two choices and the way that these results work will make sense later because they are the compact objects inside larger categories. Yeah, so that's a remark. So let's say, like, so if I write TC inside T, the subcategory of compact objects, then it turns out that fin is just the compact objects here, and finally generated modules are just the compact objects. So that's something I want to mention for later. And usually you need to work with nice properties with these categories, which could mean to explain some adjectives, like I should say rigidly, compactly generated. I don't want to get into these details now. If I have time and the opportunity, I will say something about all these adjectives. Okay, so let me move to board 5. So once you have this structure, a tensor-triangulated category, you can look at different types of subcategories in the same way we did last talk. So the type of subcategories we will be interested. They are thick, which already appeared last day. So in this language, a thick subcategory will be a triangulated subcategory. So it's close under the triangles and the cofiber sequences, and so it's a triangulated subcategory. Let me say full. Will be a full triangulated subcategory. When I say triangulated subcategory, I won't give a precise definition, but essentially means that if you have two objects which fit in a triangle, and they are in the subcategory, the third object has to be in the category, so that the triangles which contain objects in the subcategory, then the rest of the objects have to be in the subcategory. I mean, you can make yourself the definition. Yeah? And closed, it's a full triangle closed under direct sums. Well, that means retracts. Right, so it's closed under retracts. And then I will introduce a new definition. It's a localizing subcategory if it's thick, plus now it has to close under arbitrary coproducts. In particular under filter colimits, not necessarily finite ones, coproducts. And let me say what's an ideal. An ideal is a subcategory which satisfies the following, that if you have, so C inside T is an ideal if the following is satisfied, if given A in the subcategory and B any object, you use the monoidal structure, you just tensor product these two elements. There is no reason that this has to be inside the category, then it's an ideal when it is, yeah, when this is inside C. So this is mimicking the algebra, right? And so what we did yesterday about trying to organize, you have these problems in which you cannot classify objects up to isomorphism, not even in the topological case, not even up to homotopy, right? So you introduce a new notion of equivalence, and then the new notion of equivalence will be like two objects are equivalent if they generate the same thick tensor ideal. That could be the notion that we'll be looking at this. So we say that X and Y are equivalent. And classifying, we'll classify thick tensor ideals. And by classifying thick tensor ideals, then I will say why ideal does not show up in this previous context. Yeah? Yeah. Yes, because the colimit will fit in an exact sequence where you will have an arbitrary coproduct and then you quotient by some relation. So you close the coproducts and then you have an exact, you close the exact sequence and then you get the collimated thing. Yeah, it's the same argument. Yes. Yeah, exactly. Yeah. So yes. Yeah. Because I'm working in this context of tensor-triangulated. Here I'm using the exact sequences. Yeah. If you don't have the exact sequence, I think the one is the coproduct definition. Yeah, that's a good point. Thank you. So to say equivalent if only if I look at when I write this symbol means tensor ideal. That's an ideal. Yeah. So a thick tensor ideal, it's inside of a tensor triangulated category is a thick subcategory which is an ideal. So that's a thick tensor ideal. So if the thick tensor ideals they generate is the same. Yeah. So if there is one inclusion, so if the one on the left hand side is included on the one on the right hand side, that means that X can be constructed from Y. X is in this thick subcategory tensor, this thick tensor ideal. Here you have Y and naively things that you can construct from Y by using the exact sequences and using the tensor. Yeah? So if this is in here, that means that you can construct X by using these operations from Y. And then the other way around. Yeah? So that's the notion that this type of results is looking at. Yeah? Okay, so let's follow with this analogy, and let me describe a spectrum. Like we talk about ideals, right? So next step is to make sense of a notion of a spectrum in this context, and this is due to Paul Balmer. So the spectrum and then a tensor triangulated category will be called a TT category. And this is due to Paul Balmer. Yeah. So we have to define what's a prime ideal. That's the point. You define what's the prime ideal, and then the spectrum will be the set of prime ideals. That's what you do in algebra, right? So we start with a TT category, but which is essentially small. T is an essentially small TT category, and then let P inside T be a proper thick tensor ideal. We say that P is prime. If the following is satisfied, and then you could tell me the definition right now, so if one wants to try. But it's like, if you have a tensor B inside P, then A is in P, or B is in P. I mean, you could have given me this definition, right? It's like, and then what's going to be the spectrum of a tensor triangulated category is the set of prime ideals. Is the set P such that P is a prime ideal. That's it. But it has a topology. Inside that, in algebra, you have the Zariski topology for the spectrum of homogeneous prime ideals, or spectrum of prime ideals. We are going to give a topology also to this set. And with a topology, and the topology is the following. I'm going to give you a basis of closed subsets, the same way it works in some sense for the Zariski topology. So we define, given X in T, I define the support of X, which are the prime ideals, such that X does not belong to P. Yeah, that will be the support of an object of T. And this is going to give me a basis of closed subsets. Yeah, and then, and the topology is like, with the topology describe with T a basis of closed subsets. You can give also, I mean, you can use you can take also a basis of opens, but I mean, I will just give this one because it will help me later to describe some topology. And what Balmer shows, Balmer gives these definitions, but he also shows that this is a spectral space. Right? There is a notion of a spectral space mimicking the topology of the statistic topology for a spectrum of a ring. There is a general notion inside general topology described with topological properties of what's spectral space. So it turns out that this is a spectral space. And what do we do with it? Then Balmer shows the following theorem. Sorry? Oh, camera, yes. Yeah. It feels with it, yes. Yeah. I mean, when you read these definitions, I mean, they come natural, like, yeah, but, sorry? The points where X, yeah. Yeah, it's, I always, myself, I always have to think twice about this, yeah, so, but, yeah. So maybe with examples, this, yeah, you have to, depending on when you think of it from algebraic geometry, then you have to reverse the order, yes. So let me just, maybe that will clarify later with example. Yeah, so Balmer showed the following theorem. So you are in this context of essentially small tensor-triangulated category. You have this, yeah, so let's say T, essentially small tensor. Essentially small, essentially means that you have a set of isomorphism classes of objects. It's a set issue, right? Tensor-triangulated, essentially small tensor-triangulated category. We have now, okay, we have thick tensor ideals, not necessarily prime, you have all thick tensor ideals of T. On the other hand, you have Thomason subsets of spec T. And what do I mean by a Thomason subset? Thomason subset is a union of closed sets with quasi-compact complement. So quasi-compact is what I tell my students is compact. So in some fields, compact means Hausdorff and the covering thing. And quasi-compact means that any cover by open subsets is refined to a finite cover without the Hausdorff condition. But in my general topology lecture in the university, this is what I say, it's compact. And then you have Hausdorff compact. But just so then you have this map in this direction. So you take, if you have an object, well, if you have a thick subcategory, you look at the union of the supports of the objects which are in this thick subcategory. Right? You have a function in this direction. So what he shows is that this is a bijection. Yeah, so this is a classification statement which feels like the two examples up there, right? So that's all. So you can classify thick tensor ideals in a tensor-triangulated category. Let's take the examples from yesterday in terms of subsets of these Thomason subsets. Here the topology comes into play when you say Thomason subsets. Thomason subsets of this topological space, right? So you take any Thomason subset, and that will describe you a unique thick tensor ideal, and any thick tensor ideal is described uniquely by its support. So let's call this the support of C, right? So this is in this context. Essentially small means that you can apply this description. Oh, so this is back. Well, I don't want to change Blackboard. So you can apply this description. If you take the stable module category, it's not essentially small. But the compact objects are essentially small. So you can apply this result to the compact objects in the stable homotopy category and the stable module category, which are the examples which I described yesterday. Yeah? So that's a classification theorem of thick tensor ideals. So what's the job? So you can think, well, that's all. So we have a classification statement. The problem now is to describe the right-hand side. So you know that there is a topological space which classifies thick tensor ideals in an essentially small tensor-triangulated category. But you would like to give it a name. You would like to name it in the context you are working in. You want to identify this topological space with something you are familiar with. For example, with the natural numbers, if you are working with p-local, if you work with p-local spectra, you would like to describe this in terms of Moravec theories. If you are working with the module category for the group algebra of a finite group, you would like to describe it in terms of the spectrum of the cohomology ring. So that's one direction. One direction is like, now we don't have a problem of classifying, we have a problem of identifying this topological space within the context you are working in. Yeah? And the other question is that this only classifies small objects. You only classify in thick tensor ideals, and you're only working inside the compact objects in your tensor-triangulated category. So in these examples, T is TC inside the bigger T. What can we say about the bigger T? That is kind of, there are two questions now. Can we classify inside the big category? And the other question is, can we identify this topological space? Sometimes, not only as a set, but also with the topology. Yeah. Okay, so the questions now is, we have two questions to address. The first one is describe or just spec T in a given context. And the second one is just what about localizing when T is not essentially small, and what about localizing tensor ideals? Okay, yeah. So there are, well, the first thing is that, well, do we know examples? Because the two examples I gave you are for compact objects, right? Do we know examples about localizing tensor ideals in a big? And the answer is yes. Yeah. So, 3. So, and now I have the terminology to state the results of Benson, Iyengar, and Krause in the big stable module category. Yeah, no, that's okay. Yeah, so I'll. Yeah, so. So the work of Benson, Iyengar, Krause. So I'm just following this list. This is the top board is for the small objects. What we know about the big objects, right? So the objects, so says that have localizing tensor ideals in step mod G, and now G is a finite group, any finite group. They have a bijection with there is a notion of support which it's inside this theory. It has to do with the theory of representation theory. With subsets of so let's K just for simplicity. It's K is FP, which is take a prime, and that P divides the order of the group, of course. Yeah. So in that case, the situation is have localizing tensor ideals. Now we know what's a localizing tensor ideal. So you can classify all localizing tensor ideals by taking subsets, any subset of the spectrum. Here you don't remove the maximal ideal. The maximal ideal can appear as the support of a localizing subcategory. Any subset of the homogeneous prime ideal spectrum of the cohomology of G. So I mean, you just take any subset, and you know that there exists a localizing tensor ideal, a unique one, which corresponds to this subset through this theory of support. And why? And for now, I could just make a correction there at the front. Here. So here I said G is a finite P group, and I wrote thick subcategories. For any G, what happens is that you have to add thick tensor ideal tensor ideals in KG with specialization Krause subsets of brush. And the reason is that when the group is a P group, when it's a finite P group, there is a one, it's monogenic. This category is generated by a compact object, and what happens is that all thick subcategories are tensor ideal for free. So you don't need to write the tensor ideal here because it's for free, right? But if G is not a finite P group, I mean the category, this stable module category doesn't have a single generator, and then you need to write tensor ideal here, right? So now I have could correct this front up. Okay, so this is an example, and then what they did is that they developed a theory for tensor-triangulated categories, which is previous to these results, but they also, what they do is they develop a notion of stratification for triangulated categories with an action of a ring. And they define I'm not sure I will give the definition today. Maybe I will, maybe I can give some ideas. The idea, so they develop a notion of stratification. They give a definition, and the definition encodes the two key properties that your support function needs to satisfy just to derive the bijection between these two sets, right? And they say that T is stratified if there are two conditions. One is called the local to global principle, and the second one is about minimality. I will try to explain it in words because the description is quite technical, but the local to global principle somehow is telling you that they recover each object T from, you can kind of split this object in the part of this object that you see at every prime. And the local to global principle tells you that you can reconstruct T from the information at each single prime. Yeah. So I know that probably what I'm saying is just just very mystic. But the idea is that okay, so you have this unit of the symmetric monoidal structure, and then the idea is they develop a theory in which you can split this unit with idempotence related to each prime ideal. And then you use this idempotence, you split the unit in the information encoded at each prime, and then taking an object, you can tensor with each of these idempotence. And then the feeling is that you can split any object in the part, you can isolate the part which is supported at each prime. And the local to global principle is telling you that you can go back, that you can reconstruct your object from this local information at each prime. So let's, you can say it's like you can, for each T, you can reconstruct T from, let me write T sub P, and there's a formal definition what I mean by this T sub P for each p in the support of T, where T sub p has the support of this T sub p is just p. It's like you can isolate the information at each object at each prime, and the local to global principle is tell you that you can recover, in fact, T for the information isolated at each prime. And the minimality is saying that, let's say, okay, I'm going to use the annotation for each prime. Here the primes are the primes in the spectrum of this ring which acting on the category. But later on, it will be the Balmer spectrum. And for each T, you can look at the category, this subcategory, these are the objects, sorry. These are the objects which their support is this single prime. So you look at objects T such that the support of T is just a single prime. Yeah. So if you look at the objects which are supported at a single prime, this is a minimal. Localizing tensor ideal. So they describe these two conditions, and if these two conditions are satisfied, then you get this bijection for free in your context. So you have in your context, you have a notion of support, you have a way of splitting the information of the objects at the primes where the support lives, and then there are two conditions that you need to check. You don't have to go through all the technicalities of showing that this is an injection and this is a surjection. You check these two principles, and this guarantees that this is going to be a bijection, that you will be able to classify your localizing tensor ideals using subsets. In this case, it will be the spectrum of this ring. This ring will be a graded ring. So that the key point in their work, for me at least, is that they are able to isolate on all these different proofs that were in the field, and in different fields, they managed to isolate the two key properties that your support function has to satisfy: this local to global principle and this minimality. Right? Yeah. Because this will correspond to the localizing tensor ideal, which corresponds to the P. Yeah? This has support just P, and you don't want to have anything smaller, because otherwise there is nothing. P is a point. You don't have anything smaller than a point. So this has to do with surjection, and this has to do with injection. Yeah. Yes. Yeah, so you fix a prime. In this case, it will be a prime in this spectrum, and in general, it will be a prime in Balmer spectrum. And you look at all the objects whose support is this single prime, nothing else. That the support of the object is a single prime. That all the information if this object is captured by this single prime. And this gives you a localizing localizing tensor ideal. You don't know this yet. You will know why, because the support function will satisfy certain properties. And then you want this to be a minimal localizing tensor ideal. You don't want to have any localizing tensor ideal smaller than this, right? Because otherwise this would hit the same support, and then you would not have an injection, right? Unless it's empty, like it's just a zero object. Yeah? But the zero object has support, the empty support. Yes. Yeah. Okay. So that's the picture for, and then just I'll give another example. Yeah. Okay. So this is 5. So yeah, so they say, so a category is stratified if these two conditions hold. And then as a corollary, you have the classification of localizing tensor ideals, and then you also have, by restricting to compact objects, you also have classification for the thick tensor ideals. Yeah, they come together under certain hypotheses. Yeah? Okay, so another example. Yeah, so yeah, of a situation in which you can classify big objects, I mean localizing tensor ideals, comes just to advertise some of my work. Just if you take a commutative ring spectrum, and then you think of a spectrum, and then for those who don't know, it has a map from the smash with itself into itself, R smash R into R, which has the nice properties for being a ring. That should be called a ring. Yeah. So, and then you can consider, and then you can think of a spectra which is a module over this ring. So you have a map from R smash M into M, like copy the idea from algebra, and then you can make sense of the category of module spectra over this ring spectrum. So this, yeah, so, and then I don't want to go into the thing there. You can make everything work in the category of infinity. You can look at the infinity category of module rings, but just keep it naive the way it is. So this also has tensor-triangulated category. It's inside the spectra, and then you just consider a special spectra with some extra structure, right? And if you look at the homotopy, the stable homotopy of this spectrum, this is a graded ring, graded commutative ring, yeah. And then what we show is that in this context, this category is stratified in the sense of Benson, Iyengar, Krause. So that's and but I have to tell you where the support lands. Yeah, so that's, and the support using support functions that go from mod R into spect. This is a graded commutative ring, so you look at the homogeneous prime ideals of the homotopy of the ring. And then you have bijections between localizing tensor ideals, thick tensor ideals inside the category of compact objects in this module category, which will be the finite spectra and the all finite spectra. And it goes by checking that you have this, you have a support function which is well behaved and such that it satisfies these two properties. It's kind of a recipe. You have a support function which is well behaved. Tomorrow I'll tell you which means well behaved, and that satisfies these two options. These two, and then this includes an example which I like because I come from unstable homotopy theory. So this is, some of this is also new for me. So an example comes from geometric cochange on the classifying space of a finite group, or even can be a compact Lie group in that case. Yeah? And what I mean by this, means the function spectrum from the suspension spectrum of Bg, and the Ellenberg-MacLane spectrum for FP. So this is an example in which you can apply this theory, and this theory in that case, mod, cochange, BG are kind of related to the stable module category. So in the case in which G is a finite P group, for example, this is related to some category of injectives, which is related to the, I mean, this is an example, a particular case for this result, which following several equivalencies within categories, it's related to the stable module category for the modular representation theory of G. Okay, so my plan for tomorrow is trying to tell you when you can also classify localizing tensor ideals using the Balmer spectrum, and what can you say about the Balmer spectrum. That's my plan for, not tomorrow I think, but for next talk, yeah. Okay, thank you.